Questions of chapter number 4. Here is example number 1. In example number 1, we need to find out the total energy that is required to move a charge of 2 millicoulomb from point Q 680 to point P 000 against the electric field intensity 2xAx plus 4yAy voltmeter. So we will move a charge of 2 millicoulomb from point Q to point P against the electric field given electric field intensity, and we shall calculate the total amount of energy which is required to do so. In the topic of line integral, we concluded that we can choose any path between these 2 points for the sake of our convenience. We can consider a straight path between these 2 points to move the charge from point Q to point P, or we can consider straight line segments between these 2 points, or we can consider a circular path between these 2 points. So for the sake of convenience, we will consider the straight segments between these 2 points, and we will move the charge along the segment C1 from 680 to 080, and then along the straight segment C2 from 080 to 000. So we will consider the path C1, and we will calculate the energy which will be required to move this charge along this path C1, and then so we should consider the 2 straight segments C1 and C2, and we shall calculate the energy which will be required to move this charge of 2 millicoulomb along the segment C1, and the amount of energy which will be required to move this charge of 2 millicoulomb along the segment C2, and then we shall add these 2 energies, and the addition of these 2, the summation of these 2 energies will give you the total energy. So let us consider this path C1. So we consider the path C1 over here, and you see if you consider the path C1, y along this path is constant, which is 8. So definitely dy will be equal to 0. Similarly, if we consider this path C1, z is 0 as well. So z along this path is 0. It means that dz will be equal to 0. And you see x is changing from 6 to 0. So x is changing from 6 to 0 along this path. So only x is changing, y is constant, and z is constant along this straight segment C1. We know that the differential length vector in the rectangular coordinate system is given by dxax plus dyay plus dzaz. So as dy is 0 and dz is 0, definitely the differential length vector will be equal to dxax. So this is the differential length vector, and here is the electric field intensity, which is 2xax plus 4yay. So we calculate E dot dl. We calculate E dot dl. So E dot dl will be equal to 2x dx, and the energy which is required to move this charge of q coulomb along the segment C1 will be equal to minus q into the integration of E dot dl. We put the values over here. So W1 will be equal to minus 4 into 10 raised to power minus 3, and then we have the integration of x dx, and x is changing from 6 to 0. So the integration of x dx is x square by 2. If we simplify this equation, we get the energy, which is 72 millijoule. So this much energy is required to move this charge of 2 millicoulomb along the first straight segment C1. Now we consider the second straight segment. Let us consider the second straight segment, which is C2. And if you consider C2, x is 0 along C2. Similarly, z is 0 along C2. Only y is changing from 8 to 0, right? X is 0 along C2, z is 0 along C2, and only y is changing. So we consider the second straight segment, that is C2. So let us consider C2, and you see x is 0 along C2, definitely dx will be equal to 0. Similarly, z is 0, so dz will be equal to 0, and y is changing from 8 to 0. As the differential length vector is dx plus dy plus dz. So the differential length vector will be equal to dy, and then we calculate E dot dl, and this E dot dl will be equal to 2y dy. I mean, this equation is incorrect. Please correct this equation. This is not 4y dy. This is 2y dy. Okay. So E dot dl results in 2y dy. So we calculate the energy with the help of this particular equation. W2, the energy which is required to move this charge of 2 millicoulomb along the second segment. Sorry, this equation is okay. I'm sorry, this equation is okay. Okay, don't correct this equation. This equation is 4y dy, so this equation is okay. So what we do, we calculate the energy with the help of the integration minus q, and then we have the integration E dot dl. So we put the values, and W2 will be equal to minus 8 into 10 raised to power minus 3, and then we have the integration of y dy, and y is changing from 8 to 0. So you see the integration of y dy will be equal to y square by 2. So if we put the values in the second last equation, we get W2, and W2 will be equal to 256 millijoules. So if you want to calculate the total energy will be equal to W1 plus W2. So W1 plus W2 will give you the total energy. So the total energy will be equal to W1 plus W2. We have 256 millijoule plus 72 millijoule. Add these two and you guys get the answer. All right, okay. So we do example number 4.2. There are 2 points. Point Q, which is 680, and point P, which is 0, 0, 0, are located in the electric field intensity 2xax plus 2yay. Find VPQ. Okay, so you see the potential difference between these 2 points is basically the energy. The energy which is required to move a charge of 1 coulomb from point Q to point P. And you see we can choose any path between these 2 points. We can consider straight line segments, or we can consider zigzag path, or we can consider circular path. So we can consider any path for the sake of our convenience. So let us consider the straight line segment between these 2 points. So we consider C1, the first straight segment, which is C1, and you see uh, we basically we will move the charge from 680 to 080, and then from 080 to 000. So we have got two straight segment, C1 and C2. Let us consider path C1. If you consider path C1, y is 8, right? So y is not changing, y is 8. As y is 8, definitely dy will be equal to 0. Similarly, z is 0 along this particular path. As z is 0, so definitely dz will be equal to 0 as well. And only x is changing. So x is changing from 6 to 0. So definitely the differential length vector which is given by this particular equation will be equal to dx ax, and we calculate E dot dl. So E dot dl will be equal to 2x dx. So we calculate, you see, the energy along the first straight segment C1 with the help of this particular integration, and we represent this energy by V1 now, because we are going to calculate the voltage between point P and point Q. So V1 will be equal to minus the integration of E dot dl. So let us integrate E dot dl. So we have the integration of we have the integration of minus 2x dx, and x is changing from 6 to 0. The integration of x dx is x squared by 2. If we put the values over here in this particular equation, we get V1, and V1 is 36. Then we consider the second straight segment. Let us consider the second straight segment C2. So we consider this particular straight segment which is represented by C2. And if you consider the second straight segment, x is constant over here, which is 0. So x is 0 over here. Similarly, z is constant along this particular segment. Z is 0. Only y is changing, and you see y is changing from 8 to 0. Is it clear? So let us explain this path over here. So you see, we consider the second path over here, path C2. X is constant along this particular path, which is 0. Definitely dx will be equal to 0. Similarly, z is constant along C2, which is 0. dz will be equal to 0. Only y is changing from 8 to 0. So the differential length vector, which is basically equal to dx ax plus dy ay plus dz az, will be equal to dy ay. And we calculate E dot dl. So dl is dy ay, and let us consider E. We consider E. So E is 2x ax plus 2y ay. So E dot dl, gives you 2y dy. And in order to calculate the energy which is required to move a unit positive charge along the second straight segment C2, we integrate E dot dl. So V2 will be equal to minus the integration of E dot dl. Let us integrate it. So we have minus 2 the integration of y dy, and y is changing from 8 to 0. And you see the integration of y dy is the integration of y dy is y square by 2. And if we put the values over here, V2 will be equal to 64 volt. So the total energy which is required to move a unit positive charge from point Q to point P will be the potential difference between these 2 points. So the potential difference between these 2 points will be equal to V1 plus V2, and V1 plus V2 will be equal to 100 volts. So the potential difference between these 2 points is 100 volt. Okay. We consider 2 points. Point B, which is 086, point A, which is 043, are located in the electric field intensity of a point charge. So they are located, these 2 points are located in the electric field intensity of a point charge, and the magnitude of the charge is 4 nanocoulomb. If this charge is located at the origin, then find VAB. We need to find out, you see, the voltage between these 2 points, and then we need to find out VA if V is 0 at infinity. Okay, so as the charge is located at the origin, so the distance between the charge and point A is 5 meter. You see, consider point A, which is 043. The charge is located at 000, so RA is 5 meter. Similarly, the distance between the charge and point B is 10 meter. So RA, which represents the distance between the charge, the distance between the source and point A is 5 meter, and RB, which represents the distance between the source and point B, is 10 meter. We know that the potential difference due to a point charge is given by the first equation. So the voltage between point A and B due to the point charge will be equal to Q divided by 4 pi epsilon. यहाँ पे epsilon not आ जाएगा. We will assume that everything is in free space. Then we have 1 over RA minus 1 over RB. We put the values in the first equation. So if we put the values in the first equation, we will get 36 into 1 over 5 minus 1 over 10. And the voltage between point A and B due to the given source will be 3.6 volt. Now we do part B. So if the absolute potential is 0 at infinity, then the absolute potential at point A can be calculated with the help of this particular equation. VA will be equal to Q divided by 4 pi epsilon, or A. You guys will have to consider epsilon naught. Why? Because we shall assume that everything is in free space. Okay, so we put the values over here, and if you guys put the values, the absolute potential at point A with respect to infinity will be equal to 7.2 volt. Okay, we consider example number 4. There is an error in example number 4. You see, the point is 400. So don't consider this point 400. Assume that this point is 1000. So there is a small mistake in this particular point. Consider that the coordinates of this point are 10, 0, and 0. Right? So instead of 4, we have got 10. So let us assume that this point is 1000. So this point is located at in the electric field intensity of a line charge, and the line charge density of the source is 20 nanocoulomb per meter. If this line is located at y is equal to 0 and x is equal to 0, another mistake over here. this is x. Okay, so this line is located at x is equal to 0 and y is equal to 0, and um, you see the line is extending from x is equal to minus 1. No, this one is okay. Sorry, this one is okay. So the line is located at y is equal to 0 and z is equal to 0. The line is located at y is equal to 0 and z is equal to 0, and x is changing from minus 1 to plus 1. Find the absolute potential at point P. Okay, everything is okay in this particular statement. Only the point is not correct. The point is 10, 0, 0. Okay, the rest everything is okay. So let us consider the line charge over here. And you see the line charge is extending from x is equal to minus 1 to x is equal to plus 1. Here is the point under observation, and this point is 10, 0, 0. So we consider a very small portion of the line over here, which is represented by dl. Definitely dl will be equal to dx. R1, which is the position vector of the small portion of the source, will be xax. So R1 will be equal to xax, and R will be equal to 10ax. So this R1 will be equal to xax. This will be your R1. R1 will be equal to xax, and R will be equal to 10ax. Okay, so R will be equal to 10ax while R1 will be equal to xax. Now we know that, look at the equation on the top. We can calculate the absolute potential at the given point with the help of this particular integration. We have the integral of rho L dl by 4 pi epsilon r, and then we have r minus r1. Okay, what is r minus r1? R minus r1 is the distance between the small portion of the source and the point under observation. We will consider epsilon naught over here. We will assume that everything is in free space. So definitely dl will be equal to dx. R minus r1 will be equal to 10 minus x. Okay, if we put the values in this integration, if we put the values in this particular integration, if we put the values in this particular integration, so let us put the values. If we put the values in this particular integration, the absolute potential at this particular point will be equal to minus 20 into 9. Then we have the integration of minus dx divided by 10 minus x. Well, dx indicates that x is variable, so definitely x is changing, and x is changing from minus 1 to x is changing from minus 1 to plus 1, and the integration of minus dx by 10 minus x is log of 10 minus x. So if we simplify this particular equation, we get the absolute potential at this particular point, which is 36 volt. Okay, so Okay. We consider example number 4.5. The point P400 is located in the electric field intensity of a line charge. The line charge density of the source is 4 nanocoulomb per meter. If this line charge is located at y is equal to 0 and x is equal to 0, यहाँ पे सारी मैंने पिछले न्यूमेरिकल एग्जांपल में x is equal to 0 कंसीडर किया था. बेसिकली यहाँ पे गलती है. This is x is equal to 0. The line is located at y is equal to 0 and x is equal to 0 while z is changing from -3 to +3. Then find the absolute potential at point P. So we know that the absolute potential at point P will be equal to the integration of rho L dl divided by 4 pi epsilon into r minus r1. So let us consider the figure over here. You see this line charge is extending from z is equal to -3 to z is equal to 3, right? The point under observation is located on the x-axis, and this line is this point is 400. We consider a very small portion of the source, which is represented by dz, right? So definitely the position vector of the small portion of the source will be r1, and r1, which is the position vector of the small portion of the source, will be equal to z az. Okay, it will be equal to z az. This will be the position vector of the small portion of the source. The position vector of the point under observation will be equal to 4 ax. Okay, so the position vector of the point under observation will be represented by r, which will be equal to 4 ax. Okay, so let us calculate r minus r1. So r minus r1 will be equal to 4ax minus z az. Is it clear? Yes, it is clear. So if we consider rho is equal to 4, we assume that, you see, this is rho, which is basically equal to 4. So we assume that rho is equal to 4. So if this is rho, and the magnitude of, you see, r1 is z, then dl, which is the length of the small portion of the source, will be equal to dz. R minus r1 will be equal to under root rho square plus z square. Okay, so basically we assume that r is rho arrow. Rho हमारे पास जो है basically 4 के बराबर है. We assume that r is rho arrow and r1 is z az. So we consider these position vector. R1 is the position vector of the small portion of the source, which is z az, and r is the position vector of the point under observation, which is rho arrow. So definitely r minus r1 will be equal to rho arrow minus z az, and the magnitude of r minus r1 will be equal to rho square plus z square under the root. Okay, so r minus the magnitude of r minus r1 will be equal to under root rho square plus z square. we put the values in this integration. Okay, look at the integration over here. Look at the integration over here. We put the values. Where is the integration? We put the values over here in this particular integration. Let us put the values. So we put the values over here. If we put the values over here, we get 36. Then we have the integration of dz by under root rho square plus z square. And this dz indicates that the only variable on the right hand side is z, and z is changing from -3 to +3. We assume that z is equal to rho tangent theta. We assume that z is equal to rho tangent theta. If z is rho tangent theta, then dz will be equal to rho secant square theta d theta. So we put the value of dz, right, and we put the value of z in the denominator, and then we simplify it. So if we simplify this particular equation, we get 36, and then we have the integration of secant theta d theta. So if we integrate secant theta, the integration of secant theta is log of secant theta plus tangent theta. So secant theta will be equal to tangent theta will be equal to z by rho. You see, tangent theta will be equal to z by rho, and secant theta will be equal to अंडर रूट 1 ओवर प्लस टेंजेंट स्क्वायर थीटा. और उसको अगर आप लोग सिंप्लीफाई करें तो आप लोग के पास ये आ जाएगा वी पी वेल बी इक्वल टू 36 log of z plus under root rho square plus z square divided by rho, and the only variable is z. Z is changing from -3 to +3. So if we put the value of z in this particular equation, we get Vp, which is 49.9 volt. We do example number 7. An electric dipole having a dipole moment of 8 AZ nanocoulomb is located at the origin. So the dipole moment is located at the origin. Find the absolute potential at B, which is 0, 6, 8, 0. So R1, we know that the absolute potential which is caused by an electric dipole will be equal to P dot R minus R1 divided by 4 pi epsilon naught into R minus R1 raised to power 3. What is R? R is the position vector of the point under observation. So we need to calculate R, which will be the position vector of the point under observation. And what is R1? R1 is the position vector of the point where the dipole is located. So you see the electric dipole is located at the origin. So definitely R1 will be equal to 0 AX plus 0 AY plus 0 AZ. Anyhow, we know P. And R minus R1 will be equal to 6 AY plus 8 AZ. The magnitude of R minus R1 will be equal to 10 meter. So we put the values, we put the values in this particular equation. Let me show the equation once again. We put the values in this particular equation. If we put the values in this particular equation, we get the potential at the given point, and the potential at the given point will be equal to 72 Az dot 6Ay plus 8Az divided by 1000. And if we simplify this equation, we get 576 millivolt, which is the potential at the given point. Example number 4.8. 2-point charges of 2 nanocoulomb and minus 2 nanocoulomb are located at 2 millimeter 00 and minus 2 millimeter 00 respectively. Find the absolute potential and intensity at P. Point P is in the spherical coordinate system. R is 2, theta is 45 and phi is 45. Okay, so this is an electric dipole. We know that the potential due to the electric dipole can be calculated with the help of this particular equation. We have QD cos theta divided by 4 pi epsilon naught r square. So we put the values on the right hand side, and we simplify this particular equation. So we have 8 into 10 raised to power minus 12 into 9 into 10 raised to power 9 divided by 4, and we get the potential at the given point, which is 12.73. We can calculate the electric field intensity with the help of this particular equation. We have QD by 4 pi epsilon naught r cube, and then we have 2 cos theta AR plus sin theta A theta. We put the values in this particular equations on the right hand side of this particular equation. So we have 9 into 10 raised to power minus 3, and then we have 2 cos of 45 AR plus sin of 45 A theta. If we simplify this particular equation, we get the electric field intensity in the spherical coordinate system, and the electric field intensity is 12.72 AR plus 6.36 A theta. Thank you so much.